I'm very happy to have Peter Scholl speaking here today. He's an assistant professor at Aarhus, and he's been working a lot on MPC, and it's sort of crossed over into lattices a bit. So this would be a very nice talk about the intersection of these two very interesting fields. And so go ahead, Peter. Looking forward to it.
Great. Thanks very much for the introduction, Vadim. So I'll be telling you about an application of lattice-based cryptography to multi-party computation in the form of the SPDZ protocol for MPC. So this talk is not so much about some current research of mine. It's more of a general survey of the area, covering several different works. And I'd like to quickly acknowledge Carsten and Marcel for the thanks for some discussions, which I think helped form some of the insights I'll present. Okay, so the rough plan for today is to take you on a little journey of SPDZ. So starting with some background on where it fits into MPC, what kinds of tools it uses, and then moving on to describing the protocols. So I'll both look at a simplified passively secure version of the protocol before moving on to the full protocol with active security, which uses some more complex techniques like zero-knowledge proofs. And then the last chunk of this talk will be dedicated to looking at some open questions in the area, in particular a few directions which I think might be interesting and relevant for people working in lattice-based cryptography. Okay, so we're doing MPC, multi-party computation, where we have a bunch of parties with some private inputs and they want to securely compute some function, say f, across their private inputs. Do this while just learning the output of the function and nothing else on the inputs. Okay, so within the world of MPC, which is, I'm sure you're aware, a very large area, we have a lot of different types of protocols. So SPDZ is a protocol in the dishonest majority setting. So this is one of the strongest corruption settings where up to n-1 out of n parties might be corrupted at any point in the protocol. So this requires computational assumptions. You can't do things information theoretically, like with an honest majority. And additionally, if you want active security, you're limited in this case to security with a bot and no fairness. So a corrupt set of parties can force the protocol to terminate so that no honest parties learn the output. Okay, the computational model we'll be looking at is securely computing arithmetic circuits. Quite straightforward. Here we'll consider usually a finite field, say the integers modulo large prime, although there are also variants of SPDZ which can handle different things like Boolean circuits or computations of more general rings. And just so I get it out of the way, the original SPDZ protocol is based on this paper by Damgaard, Pastros, Martin, Zacharias from 2012. This was already building on some ideas from a previous protocol, this Badoza work from 2011. And then there have, of course, been many subsequent developments in the area and variations on this, some of which I'll talk more about in detail later. It's kind of the whole line of work, which I refer to when I talk about SPDZ itself, not specifically the original paper. And I'm going to try and cover as much as I can, but given there's only an hour, many apologies if there are some important works or works of your own, which I didn't manage to cover here. Okay, so SPDZ is a protocol in what we call the preprocessing model in MPC, where the protocol is divided into two phases. First, we have a preprocessing phase, which you can think of as an ideal functionality which samples some correlated randomness and gives each party one private portion of this correlated randomness. So here, each party just gets this random string Ri, and then these are used in the online phase of the protocol together with the inputs of the parties where they interact to actually learn the result of the computation. So in practice, the parties actually have to run some interactive protocol to do this preprocessing phase. But the advantage is that firstly, this can be done in advance of the computation. And secondly, doing this separation means that the online phase can be very, very efficient. So it's very lightweight. It's almost entirely information theoretic primitives that are used. And the computational cost is only around a factor of 2 on top of computing the arithmetic circuit in the clear. That's if you ignore communication, but still very cheap. Okay, so the main tool we use in SPDZ, this is mainly in the online phase, is additive secret sharing with information theoretic max. And this is a very simple kind of information theoretic max scheme where we pick a random MAC key, which is just a random field element in ZP. And then to compute a MAC on X, we just take X and multiply it with the secret key modulo P. So technically speaking, I should say this isn't actually a MAC. You can see it more of as an AMD code or something, but it's essentially used as a MAC in the protocol. So we call it a MAC. Okay, and then the secret sharing scheme that is used based on this is just additive secret sharing combined with the MACs. So whenever some value X is secret shared in the protocol, this means we have X together with the MAC on X and also the secret key, all additively secret shared between the n parties. And I use this angle brackets notation to denote that one of these values is additively shared. So each party holds some share xi, which sums together in the field to give you X. Okay, so once we have some secret shared values in speeds, we need a way to be able to reconstruct them. So the naive thing would be to just open the shares of X and reconstruct X, but then you want some way of actually checking the MAC relation. The main challenge is to do this in a way so you can check the MAC without revealing the MAC key itself. Because as soon as someone learns the MAC key, then they can forge a MAC at any stage later in the protocol, which you don't want to happen. So the way this is done is to first open X. This is just sending the shares to everyone else and reconstructing them. So there could be some additive error, say delta here. And then each party will compute this extra value called di here, where I'm going to multiply my share of the MAC key, alpha I, with the value that's been opened, X, and then subtract from this my share of the MAC on X. Now, if you look at what happens when you sum all these di things together, then if the MACs were correct, we should be just getting alpha times X minus the original MAC, so we get 0. So the parties want to just open all their commitments, sum these up, and check that this gives 0. Okay, so why does this actually give us a sound way of opening the MACs? Why can a party not cheat? Well, suppose we have this error delta in the original opening of X. Then when you compute this sum on all of the d values, what this error translates to is an error multiplied by the MAC key, because you have alpha times X prime. And since we're in a large finite field, if an adversary can come up with some corrupt shares di to make this MAC check pass, then they must have guessed alpha times delta. And the only way they can do this is by guessing alpha. And this is the part where we assume that A, we're in a field, and B, we're in a large finite field. There are ways to work around these two things, but I won't go into that now. Okay, so now we have the information theoretic max, secret sharing, and opening. We're ready for the main part of the online phase, which is evaluating this arithmetic circuit. So for every wire in the circuit, we're going to have this invariant where the value X that corresponds to the wire has been additively secret shared with these max. And because everything is linear, the max are linear, the shares are linear, if you want to do additions or multiplications by a constant, then you can just do this locally. So the main challenge where you have to rely on the preprocessing phase is in multiplication gates. So suppose we have two secret values X and Y, which are additively shared. I'm just ignoring the max for the moment, but it doesn't make a difference there. And what we need for the preprocessing is what we call a multiplication triple. So it's these three shared values, A, B, and the product of A and B, which is used to multiply X and Y. So we'll first mask and open inputs X and Y with the A and B values of the triple. And these are just random, so this isn't going to leak anything about X and Y. And then I'm going to write this product relation in a slightly different way by adding some terms which are 0 to both sides and then expanding the result. You get something a little ugly, but if you highlight some of the terms here, then it makes a bit more sense what I'm doing. So everything that's in blue here is what we've opened previously, the X plus A and Y plus B values. And then everything that's in red on the right are these A and B and A times B shares, which we have from the preprocessor. So then this is all linear in the secret values on the right, so we can just use the operations on the linear shares to compute the shares of x times y after we've done these two openings. So multiplication gates, you need one triple from the preprocessing and then two openings. And that's basically the entirety of the online phase. There's one part I missed out, which is how you actually create these shared values at the input layers to begin with. That needs a little more from the preprocessing, but it's quite straightforward, and I won't go into that now. Okay, so do we have any questions before I move on? Okay, I'll assume no. Great. So let's move on to this preprocessing phase. So we have this ideal functionality generating the triples, which we want to realize, giving these shares of AI, BI, and CI to each of the parties. So there are two main approaches to doing this in speeds-like protocols based on homomorphic encryption. One of them is a slightly earlier Bedoza method I mentioned earlier, which actually uses linearly homomorphic encryption, but then relies on a pairwise communication between every pair of parties to generate the triples in a pairwise manner. And the speeds approach is a little different. It uses depth 1 multiplicative homomorphic encryption. And all of the communication is via broadcast channel. Even though the asymptotic complexity is the same, in practice, it tends to scale better with the number of parties, whereas Bedoza can be a little bit faster for 2 or 3 parties in some cases. But I'm going to be talking about the speeds approach here, of course. Okay, so the main tool we use is a homomorphic encryption scheme with this threshold property. So here we have some algorithms, keygen, encryption, and distributed decryption, where actually both the key generation and distributed decryption will be interactive protocols. And the scheme has a plaintext space ZP, where P is the modulus for the arithmetic circuit we want to compute. And a bit more notation here, I'll have these square brackets to denote encryptions of a plaintext value A. So we need the scheme to be somewhat homomorphic, where we just need a linear number of additions in the number of parties and one multiplication on ciphertext. And we have a keygen protocol, which creates some setup where we have a common public key known to all of the parties, and then a secret key, which is additively secret shares, where every party has some share, say SI, of a secret SK. And the distributed decryption protocol, which takes these keys set up together with the ciphertext, and then is a protocol the parties run so that they can recover the original message. Okay, and today I'm just going to focus on the rest of the scheme, but not the key generation setup. Okay, so we can instantiate this from basically any lattice-based encryption scheme using LWE or ring LWE. They all have the right properties we need for this. So what most papers use is some variant of BGV or the kind of standard ring LWE based encryption scheme by now. So we work over this polynomial ring, which is polynomials of the integers modulo x to the n plus 1, where here n is a power of 2, so it's a 2-power cyclotomic. As well as the plaintext modulus p, we have a ciphertext modulus q, and then some small distributions to sample the secret key and some error terms from. And the plaintext space is going to be the ring R reduced modulo p. And if we choose the parameters carefully, then we can use this Chinese remainder theorem to decompose RP so that it's a direct product, giving us n copies of ZP. So this means the plaintext space is not ZP itself, but it's actually vectors of length n over ZP. So then the key generation algorithm. This is the basic key generation, not the actual protocol. We'll sample a public key, which is just a ring LWE sample, so random A, and then B, which is A times S plus a scaled multiple times by P of some small error term. And then the secret key is the secret S. And we write the public key in this form B minus A just to simplify things a little later. Okay, then encryption, the details are less important here, but basically to encrypt a message M, you take the public key and then you re-randomize it using ring LWE again, where if we multiplied the public key by some small polynomial U, which is kind of like another secret key, then added on some noise terms and added on the message to one of the last entries. And then decryption equation, this is more important here. To decrypt a ciphertext C0, C1, we can compute C0 plus C1 times the secret key. And if you work it out, what this gives you is the message with some additive noise term, which has been multiplied by P. So we just reduce this mod P to recover the message. Okay, so because the linearity of decryption, this has immediately linear homomorphism, so we can do some additions, which is what we want. And then we can also get one multiplication from this directly if we allow a small amount of ciphertext expansion. And the nicest way to see this is by viewing the ciphertext as a polynomial. So the C0 plus C1 times by X, that should be. And then you decrypt this by evaluating the polynomial at the secret key. So that means if you want to multiply two ciphertexts, you can just multiply their polynomials. So now you get a degree 2 polynomial instead of degree 1 polynomials, with the caveat that now the decryption procedure additionally requires knowledge of S squared. So in this key generation setup, we're actually going to require additive shares of S as well as additive shares of S squared if we want to do distributed decryption. Okay, so then the distributed decryption protocol. Let's suppose we have a ciphertext, which here is just a kind of input level ciphertext. It hasn't been multiplied, and we want to decrypt it. Then the kind of naive thing to do is, okay, we can just compute this linear operation in the secret key. We have shares of S, the ciphertext is public, and then we can open this. Now, the problem here, of course, is that when you look at this, we have this noise term, E prime here. And this noise actually depends on the secret key. And if no one knows the secret key, we don't want to reveal some information about this to the parties. So the naive solution here is to use this noise drowning technique, which if you've been to some of the other talks this week, you've probably seen this in other contexts, where you're going to drown out this small error E prime with a much larger error by adding on P times by a shared value E tilde, which is going to be super polynomially larger than the maximum value of the E prime noise we're trying to hide. So to do that, each party can just say sample locally some share of E tilde and then add this up when revealing the ciphertext. And in practice, you need this to be about, say, 2 to the 40 or 2 to the 64 times bigger than the noise bound of your ciphertext. Okay, so how do we use this to generate multiplication triples? Well, given all these things, the basic protocol is pretty straightforward. So each party is just going to sample some random messages, AI, BI, and CI prime. I'm calling it here just to differentiate from C, which comes later, and then broadcast encryptions of each of these shares. Then all parties will take the ciphertext and add them up to produce encryptions of A, B, and C prime using the homomorphic operation. Then we'll multiply A and B together, again with homomorphism, and then subtract the encrypted value C prime, which the parties generated in the first place. And what this gives us is some delta between the original C prime shares they generated and the actual product of the real shares A and B. Then we run the distributed decryption on this shared delta, and that allows the parties to then adjust the original random shares they sampled to lead you to a correct additive sharing of a multiplication triple. So actually the only party who needs to change anything is, say, party P1, who just takes the C1 prime share, adds on delta, and adjusts it so they have a correct triple. So this is a kind of passive protocol without any max. If you want to add the max, then you can essentially do the same procedure where the parties, they already have the ciphertext encrypting the shares of the triple from the first phase, so you just need an encryption of the MAC key. Then you do the same multiplication followed by distributed decryption. Okay, so that's the simplified version of speeds. Once you have the threshold homomorphic encryption, that should be straightforward. Do we have any questions?
Peter, can I ask you a question?
Yeah, sure.
So we were adding this droning noise, right? So things you were encrypting, those are your the triples basically you'll be using the online phase. And each one is only used once, yes?
Yes, that's right.
So even if you leak something about it, it's sort of not super catastrophic. I mean, and sort of, I don't see what you can prove, but it's not super catastrophic if you leak, just a little bit. So when you're drowning with 64, maybe you can drown with a little less and prove, I don't know, that you're not revealing that much
actually,
information.
you're coming on to something which I'm going to talk a bit more about at the end. But just to quickly say now, I'm not sure whether you're talking about leaking on the secret key or leaking on the triples themselves. I assume you meant the secret key, right?
Let's see. Yeah.
Because in the online phase,
a different secret key.
Yes, because if you have a triple which is not uniformly random, then this will actually leak information on maybe some of your inputs in the online phase. So you really need the triples to be completely random, no leakage. But the secret key, maybe you can tolerate something.
And you can choose a different secret key for each encryption, right? Or
yes, exactly. Yes. Yeah, I'll have more on this later.
Okay, thanks.
Okay, so let's move on to active security. So there's basically two main changes we need to make to the passively secure protocol to make this actively secure. The first one is adding in zero-knowledge proofs of plain text knowledge. So every time a party broadcasts some ciphertext saying this encryption of AI, then I need to run a zero-knowledge proof where I prove that I know the underlying message AI together with the randomness which was used to encrypt it. So this ensures that all of the ciphertexts were correctly generated and nothing can go wrong there. So then we still need to do one more step on top of the zero-knowledge proofs, which is add some actual verification procedure to check that the triples themselves are correct. Now, the reason for this is that there could be some extra errors introduced during the distributed decryption process. So recall we did this distributed decryption on A, B, and C, and then we use these shares again to multiply in the MAC key in a second iteration. So it could be that you might get additive errors in the C term after it was decrypted, which will then be introduced when you multiply with the MAC key in the next step. So the way to verify this is just to perform what we call a sacrifice check, where you take one multiplication triple and then use it to check the correctness of another. So it involves some random challenge in the field, which gives you some soundness error 1 over the size of the field. It's basically a factor 2 overhead. So the main thing of interest, I think here, and especially maybe to this audience, is the zero-knowledge proofs that are used for the ciphertext. So I'll move on to those a little bit now. So recall the encryption equation. We had this 2 ring element ciphertext, which is encrypted by taking the public key minus BA, multiplying it by some small polynomial, adding some noise, and then adding the message. Okay, so we can massage this a little bit into a nicer looking linear relation, where on the left we have a matrix which consists of the public key and some public values, and on the right, all of the randomness of the message that's secret in the ciphertext. So what we want to do is just prove knowledge of some short preimage that satisfies this linear relation. So we have some known bounds on the sizes of, say, the noise terms and the message we want to verify. We want to prove that this holds. So thankfully, there's a lot of techniques for doing this that have been studied over the last few years, mostly building on work of Vadim and others. And they all follow this kind of standard Schnorr type Sigma protocol approach with this 3-move protocol between a prover and a verifier. So if you want to prove knowledge of the secret R, then the prover in the first message will generate a fresh random ciphertext with different randomness R prime. And the verifier responds with a random challenge. In this case, let's just say it's binary. And the prover sends back this value z, which is either the randomness r prime or the sum r prime plus r. So then the verifier at the end will have to check firstly that z is short, as we want, and secondly that z satisfies the linear relation, which is going to be defined by c plus c prime, or c prime plus e times c. And if this holds, then this should be a good proof. So we have binary challenges, which you can show this. This gives you soundness a half. So given 2 accepting transcripts, you can extract some short witness from the prover. But the more challenging thing here is that this final value z you're sending, just like the distributed decryption, this might involve some leakage on the secret. Because you're masking r with r prime, in the case e equals 1. And if these both have the same size, and because they're small and there's no wraparound, then that's going to leak something. So the 2 kind of standard options you can do to address this are either rejection sampling, which is kind of complex and adds some computational overheads, but can work well. Or you can do the more naive noise drowning again, where you just choose r prime to be superpolynomially larger than r. The problem with noise drowning here is that this introduces this soundness slack parameter into the proof, where if you choose r prime to be very, very large, then a dishonest prover can also choose r to be much larger than what you want it to be and still pass the proof. Which means in your encryption scheme, you need the modulus q to be much larger than you would normally with the passive protocol, and gives you bigger parameters. But in practice, if you look at all of the speeds implementations out there, as far as I know, they all actually follow this noise drowning approach, I think mainly just because it's simpler to implement. I'm not sure of actually any comparison between the computational efficiency in the case of speeds here. Okay, so you can do some optimizations to this basic approach. A natural one is to go for a larger challenge space. So this Top Gear protocol, also building on previous work from Vadim and others, chooses challenges from which are powers of x instead of just binary, which gives you some better soundness. It means you don't need as many repetitions. The slight thing to watch out for here is that it doesn't prove that the secret r is exactly short. It proves that 2 times r is short. It turns out you can tweak the protocol and make this work, and for speeds, that's not a problem. And then another, I think, very important optimization is amortizing proofs. So with a naive kind of binary challenge space, or even with the powers of x challenge space, you still have to repeat this proof many times and send a new ciphertext for each time you want to prove. So if you have many ciphertexts you want to prove at once, say if you're creating a very large batch of triples, with amortization techniques, you can reduce this multiplicative overhead in the security parameter from repetitions to just an additive overhead. So this greatly reduces your communication complexity down to just a constant factor on top of the passive protocol instead of multiplicative. Okay, so that's the basic zero-knowledge proof and the actively secure protocol. Now I'm just going to talk about a few different variations on the general protocol. There's, as I said, a lot of different works which have looked at this and done things differently. I'll try and mention a few of them here. So firstly, this recent work on ePrint by Howard Chen and others, where they took speeds and tweaked a few things about it. They used depth 2 somewhat homomorphic encryption instead of depth 1. So you actually need 2 multiplications to get the MAC key. And what this does is instead of doing a distributed decryption after the first multiplication so that you can support depth 1, you only do a single one at the end, which means you can avoid the sacrifice procedure when you generate triples. You can also use scale invariant homomorphic encryption instead of BGV. There's probably some trade-offs there. I'm not sure about a direct comparison. And you can also use fancy things like the automorphisms and homomorphic encryption schemes to generate more complex types of preprocessing data like matrix triples, for example. And there's another variant of distributed decryption, which I want to mention, which is only applicable to the two-party setting, but I think it's quite interesting. Instead of having this interactive protocol with noise drowning, you can just have a local rounding procedure. So we're given a ciphertext and shares of the secret key. Everyone can just locally compute the shares of this decryption and then kind of round this to get, which results in a share of the message. It doesn't recover the message itself, is non-interactive, but you get a share of the message and you can adapt speed so that you use this instead. One problem with this is it still needs a super polynomial modulus. Even though you don't have noise drowning, you actually get a kind of correctness error from the rounding if you don't have a big gap between the message size and the modulus. And this comes from spooky encryption and homomorphic secret sharing techniques. Finally, you can also throw at these key switching and modulus switching strategies, which are often used in fully homomorphic encryption. So I'm not totally clear about the different trade-offs with key switching, but I think modulus switching can, in some sense, reduce the overhead from the soundness flag in the zero-knowledge proofs. If you just do noise drowning, then if you modulus switch before multiplying, then it reduces the blow-up of this extra soundness flag parameter you had in the modulus, so that it doesn't become quadratically worse after multiplying. Okay, so now I plan to move on to some open questions and possible directions, unless there are any more questions about the protocol. Okay, great. So before moving on to the concrete directions I've been thinking about, I just want to say, okay, what are the areas we can hope to actually do better in this protocol? Well, I think one significant thing is the parameters of the homomorphic encryption scheme. So if you look at some example parameters, you typically have, say, plain text space, which is maybe between 64 and 128 bits. And with all of the noise drowning and the zero knowledge and distributed decryption procedures, this gives you a modulus of between maybe 300 or up to 600 bits, depending on other parameters. And the dimension in the ring is usually around 16,000 or maybe 32,000. So this is kind of close to the FAG level of parameters, even though we're only doing one multiplication. And then related to this, I think a significant thing of interest is the zero knowledge proofs of plain text knowledge. So as I said, we have these amortization techniques, but if you want to get the best out of them, then you need to be creating a large batch of triples in the first place. And since the ciphertexts are already so big, like 16,000 or something, then if you have to repeat this 40 times to get efficiently, then you're already generating close to 1 million triples. And if you don't want to do a batch size that big, then you don't really have any other option at this point. And secondly, these proofs are quite expensive. I'm told it's about 40% of the runtime. I think in some areas, it might actually contribute a lot more. So in particular, using these proofs of knowledge actually means the communication complexity of this protocol has to be quadratic in the number of parties. So I didn't mention it at the time, but the passive protocol, if you look at it, everything that's sent over the network, all you're doing is basically sending some ciphertexts, summing them up, and then computing the results. So naively, that's quadratic, but you can always optimize this by just sending the ciphertext or the shares to one party, sums up the shares locally, and then sends back only the result to everybody else. So with that, the entire passive protocol can be linear in the number of parties. And that's both the offline and the online phases. Whereas here, as soon as you throw in zero knowledge proofs, which you need everyone to be able to verify to ensure no one's cheating, then we don't see how to avoid this quadratic blowup. That would be something nice to avoid.
Peter?
Yeah.
How big are the batches? So you're saying you've ended up with too many, but what is the number of these variables that you want for your MPC protocol?
Sorry, I lost.
How many of these triples? Sorry. How many of these triples do you typically need to have for your MPC?
Okay, yes. And that really depends on what you're doing. So Yeah, I think if you're doing kind of complex applications which have like a lot of, maybe not naturally arithmetic operations, where maybe you need to mix arithmetic with things like comparisons or other nonlinear operations, then to do those types of things like rapidly blows up your number of triples, and I think you can easily get into the millions. But I could also imagine there might be smaller use cases where you just have a kind of simple task you want to do, where it might be more like thousands or tens of thousands. But yeah, it very much depends.
Okay, thanks.
Okay, so
Peter, if I may,
yeah.
one more question. This is Vinod. So right now we need this noise flooding or drowning analysis in the ZK proofs. Can't we use something like the runny divergence type analysis? Perhaps if the number of the number of sort of interactions is small enough. Isn't there a better sort of analysis at this point, or
well,
not?
so I don't know about any analysis. Do you mean that by just running the proof naively with some smaller drowning noise? Because you can always do rejection sampling for the zero-knowledge proofs, and that reduces the soundness lag, but it's a little more expensive and complicated.
So there is this sort of a line of work of Damian and I believe Damian and friends, which says that instead of sort of analyzing statistical distance between distributions, you can just analyze the Rani divergence, and that's sometimes good enough for proofs. And
so I don't know if that can be applied to zero-knowledge proofs. This is also somewhat related to something I'll come to later, but I don't know the answer to that one. I have come across these works in other contexts. I'm not sure if you can use them there.
Okay, sounds good.
Okay, so the ideal goal we would like to have for zero-knowledge proofs is, of course, something where we can get negligible soundness in just a single execution, while also getting tight bounds on the size of the witnesses. Now, maybe one possible approach is to use something which Gregor was talking about the other day, and which are these types of proofs on committed values, also building on previous works, where instead of proving statements about the ciphertext directly, you can create some commitments to all of the randomness in the message in the ciphertext, prove that these commitments contain short values, and then prove that the commitments together satisfy the linear relation defined by the ciphertext and the public key. I'm not sure how much overhead there would be, and additionally committing to all of this randomness for every ciphertext you use, but it might be interesting to explore, especially if you're in this kind of small batch size setting where you don't want to create as many triples as like a million or so. And if you can also amortize this in some way so that you avoid the overhead of creating all these auxiliary commitments, then that might be very interesting.
And Peter, what is it? What is the objective that you're trying to minimize here? Is it the time, or is it the size of the commitments, or the size of the proofs, the communication complexity? What is the main objective?
So if you're in a one-shot setting, then I would say probably communication complexity, although, and it's all kind of important. If computation becomes a big bottleneck, then that's not so good. But at least as far as I know, the existing techniques for proving knowledge of ciphertexts without going via commitments, you have to do a lot of repetitions, and then the main thing that's going to get you into trouble there is the massive amount of communication.
Peter, can I ask a question? And the one here. So there's also this covered version of speeds where they don't use zero knowledge altogether, and they're using. So what is the difference? Like, of course, it's a covered security, but can you compare in terms of security? Practicality?
Well, practicality, I think covert security, it definitely has this nice benefit where if you want to do it on a small batch size, then you can do things very efficiently with essentially the overhead is going to be multiplicative in whatever your covert parameter is. So if you want the adversary to only be able to cheat with probability 1/c, you get a factor C overhead in running time. So I think if you're happy with that kind of thing, so with like C equals 5 or 10, that's definitely a good approach.
Yeah, right. So, but there they also use commitments, right? But they don't prove. Yeah, it's a bit different. Okay.
Yeah, yeah. And it's just regular commitments, not
Yeah,
special lattice-based commitments.
Yes. Okay, thank you.
Okay. So I've talked about maybe improving the zero-knowledge proofs, but I think one thing that's interesting to explore is whether we actually even need these zero-knowledge proofs in the first place. So they said we already have this triple verification procedure, which guarantees that what you have at the end is a correct multiplication triple. Okay, so what could actually go wrong if you just take out the proofs and then run speeds as is? Okay, well, I thought about this a little. The first thing that goes wrong is, okay, sorry, I'm getting ahead of myself here. Okay, so the main challenge is to ensure that in this verification step, the failure event of the correctness check passing or not has to be independent of any sensitive information, like the secret key or the underlying messages. Proving this is very difficult, but I think if you can do something, then you can avoid this quadratic complexity from the zero-knowledge proofs. You can get better parameters in the ciphertext because all of this noise drowning stuff goes away and you get much less computation, basically be a factor 2 overhead over the passive protocol. This is kind of a dream goal, which is so kind of difficult to analyze. But slightly related work here is the Overdrive paper from 2 years ago, where they did something somewhat similar by removing a proof of correct multiplication, which was in a different protocol, where they still had proof of knowledge of ciphertext generation, but they got rid of the other proof, and then proof security related to some linear-only encryption assumption, which has been used also in lattice-based SNARK constructions. Okay, so the first problem that comes across, if you do this, is that you no longer have independence of inputs. So I could just send a ciphertext, which is the same as something I received, or I can force the ciphertext to all be encryptions of 0 at the end of it by simply flipping the sign. But this is an easy one to work around with just by committing to ciphertext and then opening all the commitments together at the end. Okay, so the second problem is exactly this problem that we're verifying correctness, and this check of the triples, like the outcome of whether it succeeds or not, can be seen as a kind of decryption oracle, which the adversary might try to exploit in something somewhat analogous to a CCA attack with a standard lattice-based public key encryption scheme. But in speeds, it's actually much more restricted compared to a regular CCA attack. So we have a lot of things we can do to try to mitigate this. And as Vadim was suggesting earlier, if we do this kind of check and it fails, then the parties can all agree to just regenerate the keys and abort, not use something again. So this significantly restricts the adversary in that every time they kind of try to use this decryption oracle type thing, then they have to be guaranteed they're going to be passed. As soon as they fail, then they lose the game. So at this point, if they learn something, it doesn't actually matter if we abort because all we're doing is just random preprocessing anyway. You can also restrict the number of executions you use for any given secret key. And if you can maybe bound the leakage in some way from each possible query, then perhaps you can increase the entropy in the secret key to compensate. And finally, one thing you have to take care of is that if you're leaking anything on the actual data on the triples themselves, rather than just a secret key, then that's something that can really cause a problem in the online phase and you don't want. So but even if that does occur, there are kind of standard ways you can use to work around that using something like the leftover hash lemma as a randomness extractor to kind of extract entropy from triples. So I think there's a lot of things to look at here, and to me it doesn't seem like there's that much that can go wrong from this. I think the challenge is mainly to do with analyzing what does happen and kind of formally modeling the type of decryption queries or oracle queries an adversary can make in this. But I think it seems like a promising direction. Perhaps you could even prove some kind of security based on some entropic variant of LWE, which we actually have some at least theoretical hardness results about, I think. Okay, so the second thing I want to look at is not related to zero knowledge proofs, but actually about the noise drowning process in the distributed decryption.
Wait, Peter, can I ask you something about the previous slide?
Yeah, sure.
So do you need to, so where exactly do you need ciphertext and not just commitments and opening commitments? So is it?
So it's going to be whenever, so in the first phase of the triple generation, when everyone sends their encryptions of AI and BI and CI. Yeah, so there they just have to commit to the ciphertext first and then open the commitments after everyone has committed.
So, but why do they have to be encryptions of AI, BI, and CI? Why can't they be just commitments to them? Because they still open them anyway in a distributed fashion.
So you never open the underlying plain text which you sent to. So I guess if you had some homomorphic commitment, then you could do that.
Right. So
yes.
Okay.
But I'm just thinking like a simple, random oracle-based commitment. So it's not going to add much complexity on top of what's already there.
No, I was just thinking that if you didn't have ciphertext, if you only had commitments, then it would be easier to sort of not leak anything if you don't do zero knowledge, right? Because you leak some, if it's a statistically hiding commitment, then you leak some part of the randomness and it's probably no problem.
Right. So if you mean you replace the encryption itself with some kind of
Right.
homomorphic commitment scheme.
Right.
I see what you mean. Yeah. But then you still need to multiply the underlying shares themselves, right? And when you multiply commitments, does that give you multiplication on the values?
You can
not trivially, I guess, but you have to do something.
Homomorphic commitments. In particular, you can do multiplications, but I think, to the best of my knowledge, that's only known from sort of like GSW techniques, which probably are sort of that they'll take you to a next level of inefficiency.
Okay. Yeah. Yeah. It sounds interesting, but I'm not so familiar with these homomorphic commitment schemes that could do that. Okay, are there any more questions? Okay, so the last thing I want to talk about related to speeds is the distributed decryption, which then goes back to the question earlier about the noise drowning, or the question was about the zero knowledge proofs, but here I want to look at it in the distributed decryption lens, where we're doing this noise drowning to mask the noise in the ciphertext you open. So the first question is there any approach to doing this without noise drowning? So recovering the message in some way, and I guess you could always do a kind of generic multi-party computation to decrypt it, but that's a bit excessive. So we want something simple, which recovers M exactly. And then secondly, what actually goes wrong if we just take this approach and reduce the size of the drowned noise? So I don't know if you can use something like Renyi divergence to analyze this. It might be you can, but I haven't seen anything along these lines. Intuitively to me, it seems like a kind of difficult problem to look at the exact leakage on the secret key from this. But then also it doesn't seem like it should be that bad, because especially in this case, the secret key is always being multiplied by some random noise term E prime, which is different for every ciphertext. It's not like you're getting some kind of fixed leakage on every time this is queried. But to me, this looks like a kind of tricky thing to analyze, whether you can do it information theoretically or do some maybe computational problem that shows that it's hard to recover the S given this leakage. I don't know, but it would be great to see something looking at this problem. Okay, and the last thing I want to mention is actually a different approach to multiplication triple generation for speeds, which is a line of work I've recently been involved in, where instead of using homomorphic encryption, you look at a way of generating triples somehow non-interactively. So the goal is to start from, say, a set of correlated seeds, which are maybe distributed to the parties in advance, and that can be locally expanded to produce a much larger batch of triples. And so this is called a pseudo-random correlation generator. We had some very recent work, which actually should be on ePrint next week, I think, where we have a candidate construction from not quite lattices, but a variant of ring LPN. We have some very low Hamming weight noise with this arithmetic form, again, over the cyclotomic 2-power polynomial ring. So this is, I think, interesting alternative to speeds. And it still seems to have quite good concrete efficiency, but I don't think it's going to replace everything I've talked about today. In fact, generating these correlated seeds in the first place actually requires a whole batch of triples just to set up the seeds. So maybe something like the tens of thousands to create them in the first place. And this is also maybe a good motivation for doing these one-shot zero-knowledge proofs in this setup phase. Another thing is this assumption on ring LPN is not so well studied. I think we're the first ones to look at this, where we actually rely on having this cyclotomic ring, which splits completely into linear factors. We did a little bit of analysis, but so far it hasn't been looked at much. Also, it's not on the slide, but I should say this is restricted to the two-party setting. So we don't know how to get this kind of approach to generating speeds triples with more than two parties.
So Peter, it's LPN in the sense LPN over large fields with Hamming error,
yes,
right?
Yes,
okay.
Exactly over the plain text ring.
I see. And what does low noise refer to? Like, what's the fraction of corrupted coordinates?
Okay, so to be a bit more concrete, it means very, very low noise, say maybe order of security parameter is ideal. But this number of samples is very restricted. So it's like 2 ring LPN samples where the noise has maybe a couple of hundred non-zero coordinates.
Okay, all right, okay, I understand.
Okay, so that pretty much brings me to the end. So you've seen this tour of the speech protocol, which is at the moment at least the most practical approach to dishonest majority MPC. And we've looked at how lattices are used in speeds, where we use this low-depth homomorphic encryption scheme with somewhat large parameters, mainly due to the use of zero-knowledge proofs and distributed decryption. I think these are the areas which I'd love to see a little bit more interaction with the lattice community and see if people can come up with anything. Also be very happy to collaborate if anyone wants to reach out. Most importantly, I'm looking forward to seeing what can come out of this. Okay, do we have any more questions?
Okay, thank you very much, Peter, for
thanks, Peter. Great talk. We have 2 Peters today, and Peter number 2. No particular ordering. Number 2 will Peter Rindle will speak in about 20 minutes. So that's 11 a.m. Pacific time.
That's great. Thank you.